Hello everyone. So, today we are going to start module 3 of this course, and in the first lecture of this module I will give an introduction to eigenvalues and eigenvectors. Why I am giving this introduction to you? Because in this unit we will focus on finding the eigenvalue and eigenvectors using the numerical methods for a given matrix. Basically, in real life problems, quite frequently we need to find out eigenvalues or eigenvectors of a matrix for getting some idea about the system, and hence it is very important to know about these two things, that is eigenvalues and eigenvectors for a given matrix, and how to apply numerical methods for finding eigenvalues and eigenvectors of a given matrix. So, let me define the eigenvalue and eigenvectors. So, let A be a square matrix of order n. So, it means this matrix A is the element of the vector space C m by n. Then a non-zero vector x belongs to Rn, or more generally you can write it belongs to Cn, is said to be an eigenvector of A if x equals to lambda x for some scalar lambda. Notice this, that I will say that x is an eigenvector of A. First of all, it should be a non-zero vector. Second thing, it should be satisfy this particular condition, that is x equals to lambda x. Now, let us talk about this scalar lambda. Here lambda is called eigenvalue of A, and hence we can say that x is an eigenvector corresponding to the eigenvalue lambda. For example, take a 2 by 2 matrix two 1 2 3. So, if I take a vector, let us say 1 2, so this I can write it 4 times 1 2. So, this is my matrix A, this is the eigenvector x, this is equals to lambda times x. So, it means this particular vector 1 2 is an eigenvector of this matrix A, and 4 is an eigenvalue of A, and this eigenvector 1 2 is an eigenvector corresponding to eigenvalue 4. Now, what this equation is telling? What we are having? X is a vector and A is a matrix. So, every matrix is a transformation, basically linear transformation. So, what we are doing? We are applying a linear transformation on a vector x and we are getting a scalar change in the vector x, scalar time change. So, either the vector will expand or vector will stretch. This will depend on the value of lambda. For example, in the earlier one I was having initially vector 1 2 and after applying the transformation it is becoming 4 times 1 2, that is it is going to 4 8. So, there was a magnification in the vector of 4 times. So, hence this is the another interpretation of eigenvalue and eigenvector of a transformation or matrix A. Now, how to find eigenvalues and eigenvectors of a given matrix? So, method for finding eigenvalues and eigenvectors. Now, look at this definition of eigenvectors. Here I am saying that x is a non-zero vector and it is said to be an eigenvector of A if A times x equals to lambda x. So, A into x equals to lambda x can be written as Ax minus lambda x equals to 0, or this I can write this A minus lambda I x equals to 0, where I is the identity matrix of the same order as A. Now, from here you can see we are having a system of homogeneous equation with where we are having n equations and n unknown. I am saying that x is a non-zero vector. So, if x is a non-zero vector means this system is having non-zero solutions, and if I talk that this system is having non-zero solution, it means that is the null space of this particular transformation A minus lambda I is having dimension more than 0. Now, if this is having the non-zero solution, it should be having rank less than 1 less than n. So, rank of this A minus lambda I should be less than n. It means determinant of A minus lambda I should be 0, because if rank is less than n. Now, if I get the determinant of A minus lambda I, it will be a polynomial of n degree in lambda, and the zeros of that particular polynomial are the eigenvalue of matrix A. So, using this concept we can find the eigenvalues of a matrix. Means what you need to do? You have to write the matrix A minus lambda I. You have to find out the polynomial which is coming from the determinant of A minus lambda I, and solving this equation, linear equation, that is a polynomial in of degree n in lambda equals to 0, you will find the eigenvalues of A. Now, as I told you, by solving this equation you can get the values of lambda, for which determinant of A minus lambda equals to 0, and these values of lambda is called the eigenvalues of A. This particular polynomial is called the characteristic polynomial of A, and hence eigenvalues are also called the characteristic values of the given matrix. Now, once you find out the eigenvalues, let us say eigenvalues are coming like this: lambda 1, lambda 2, lambda n. Then what we need to do? We need to find out the eigenvectors corresponding to each eigenvalue. So, eigenvector corresponding to eigenvalue lambda equals to lambda 1, can be calculated just by solving the homogeneous system of equations A minus lambda 1 I x equals to 0. Since we have choose such a lambda 1 for which this system is having non-zero solution, and hence we will get a non-zero vector x as a solution of this system, and that non-zero vector x will be the eigenvector corresponding to lambda equals to lambda 1. Then similarly we can find the eigenvectors corresponding to other eigenvalues. So, this is the classic way of finding eigenvalues and eigenvectors of a given matrix. So, let us take an example of it. Let us consider this 2 by 2 matrix. So, first row is 3, 2, 7, minus 2. We need to find out the eigenvalues and eigenvectors of this matrix. So, the characteristic polynomial of A is determinant of A minus lambda I, which becomes 3 minus lambda minus 2 minus lambda 2 and 7 into minus 14 lambda square minus lambda minus 20, and 0 of this polynomial is 5 and minus 4. So, hence eigenvalue of this matrix is 5 and minus 4. Once we find eigenvalues, we need to calculate eigenvectors. So, eigenvector corresponding to lambda equals to 5 is given by A minus 5 I into x equals to 0, that is we got two equations, one is minus 2x1 plus 2x2 equals to 0, another one 7x1 minus 7x2 equals to 0. Basically both are the same equation, they linearly dependent, and the solution of this equation is x1 equals to x2. So, we choose x2 as 1, so x1 will be 1, hence 1 1 is an eigenvector corresponding to eigenvalue lambda equals to 5. Similarly, we can calculate the eigenvector corresponding to lambda equals to minus 4, and it is coming out 2 and minus 7. You can verify that both of these eigenvectors with respect to eigenvalues 5 and minus 4 satisfy the relation x equals to lambda x. Now, geometrically a n by n matrix A, we are multiplying it by a n by n vector x. So, resulting into another n by 1 vector y equals to A x. Thus, A can be considered as a transformation matrix, which is transforming a vector into another vector of the same dimension. In general, a matrix acts on a vector by changing both its magnitude and its direction. However, a matrix may act on certain vectors by changing only their magnitude and leaving their direction unchanged, or possibly reversing the direction. These vectors are the eigenvectors of the matrix. Okay? So, if we are having a matrix, it is we are applying this matrix on a set of vectors. For some of the vectors it will change magnitude as well as direction. However, for certain vectors what it will do, if you are having n by n matrix, there will be vectors n or less than n, for which just what it will do, linearly independent vectors. It will only change the magnitude, and those vectors will be the eigenvectors of the matrix. So, in this way we can differentiate, or we can take out the eigenvectors of a matrix from the set of vectors. So, a matrix acts on an eigenvector by multiplying its magnitude by a factor which is positive if its direction is unchanged and negative if its direction is reversed. This factor is eigenvalue associated with that eigenvector. So, you can see x equals to lambda x. We are A is acting on x and we are getting lambda x. What is lambda? Lambda is just a scalar. So, what will happen if lambda is some positive number? What will happen? The direction of the vector will never change, because if it vector is x1 x2, it will become lambda times x1 lambda times x2. If lambda is negative number, it will become just the direction of the vector becomes in the reverse direction. However, magnitude will certainly change. Just take this beautiful example. Here we are having this 2 by 2 matrix A. I am applying this matrix A on this set of points. So, after applying this transformation or this matrix on this set of points, I am getting these red points. So, blue points are before transformation and red cluster of points are after transformation. So, what is happening? It is changing this square shape point to in this shape. Now, if I calculate the eigenvalues and eigenvectors of this matrix, eigenvalues are coming 1 and 2. Corresponding to 1, eigenvector is minus 0.7071 and 0.7071, means it is something, a line in the direction of y equals to x, and here it is coming same. So, it is a line in the direction of y equals to minus x. Sorry, this is the line in direction of y equals to minus x, this is the line in the direction of y equals to x, and hence you can see what we are having, this change is the maximum in the direction of y equals to x. And what is the scale of the change? This scale of change is just double. So, what I want to say that in the direction of eigenvector corresponding to largest eigenvalue, we are having the maximum change, and change is just multiple of that particular eigenvalue, and no change in the direction of this y equals to x, because here eigenvalue is 1. So, 1 into that vector will remain the same. So, here the role of eigenvector corresponding to the biggest eigenvalue becomes very important for analyzing patterns, or in when you are talking about data analytics or pattern classification in all these areas. So, we will learn some numerical methods to find out the maximum eigenvalue and corresponding eigenvector of a given matrix in the coming lectures. Now, as I told you, eigenvalues are the roots of the characteristic polynomials, and a polynomial can have repeated roots. So, for example, I can have lambda 1 equals to lambda 2 equals to up to lambda k. So, if that happens, the eigenvalue is said to be of algebraic multiplicity k. So, what is algebraic multiplicity of an eigenvalue? The algebraic multiplicity is the number of times it is repeated. For example, if I am having a matrix 3 by 3 order matrix A and eigenvalue is 2, 3, 5. So, hence all the eigenvalues are having algebraic multiplicity 1. If I am having eigenvalues as 2 to 5, so here eigenvalue 2 is having the algebraic multiplicity 2 and 5 is having algebraic multiplicity 1. If I am having eigenvalue as 2 to 2, so 2 is repeating 3 times, then algebraic multiplicity of eigenvalue lambda equals to 2 is 3. Now, for each distinct eigenvalue of matrix A, there will be correspond at least one eigenvector, which can be found by solving the appropriate set of homogeneous equations. Let K be the algebraic multiplicity of eigenvalue lambda. If M is the number of linearly independent eigenvectors, please note that linearly independent corresponding to eigenvalue lambda, then M will be always lie between 1 to K. Means the number of linearly independent eigenvectors corresponding to an eigenvalue will be always less than equals to the algebraic multiplicity of the eigenvalue, and this particular number of linearly independent eigenvectors corresponding to a given eigenvalue is called the geometric multiplicity of the eigenvalue. So, I want to say that geometric multiplicity never exceed algebraic multiplicity. Like if you take this example, it is a 3 by 3 matrix, it is a upper triangular matrix, it is having characteristic equation lambda minus 2 cube equals to 0. So, hence it is having root 2 repeated 3 times, algebraic multiplicity of eigenvalue lambda equals to 2 is 3. If I calculate the eigenvector corresponding to lambda equals to 2, then I am getting the eigenvector 1 0 0 and 0 0 1. So, hence geometric multiplicity of eigenvalue 2 is only 2, whereas algebraic multiplicity is 3. Let me tell you some properties of eigenvalues and eigenvectors. So, the sum of the eigenvalues of a matrix equals to trace of the matrix. So, how can we define the trace of a matrix? Trace is the sum of diagonal elements of the matrix, and hence sum of eigenvalues equals to sum of diagonal elements of the matrix, and that you can see from the characteristic equation very clearly. The product of eigenvalues of a matrix equals to the determinant of the matrix. Hence, if a matrix is having a 0 eigenvalue, one of the eigenvalues is 0, means the matrix is a singular matrix, because determinant is the product of eigenvalues, 0 is coming there. So, product will be 0, hence determinant will be 0. The eigenvalues of an upper or lower triangular matrix are the elements of the main diagonal. Similarly, the eigenvalues of a diagonal matrix are the elements of the diagonal. If lambda is an eigenvalue of A and A is an invertible matrix, then eigenvalue of A inverse will be 1 upon lambda, and both will be having the same vector corresponding to same eigenvectors. If lambda is an eigenvalue of A, then K lambda is an eigenvalue of matrix K A, and these can be the proof is given very easily. Suppose you are having a matrix X equals to lambda X. Now, what you do, multiply both sides by A inverse. If A inverse exists, so A inverse X will become lambda times A inverse X, and from here I can write A inverse X equals to 1 upon lambda into X. So, if X is an eigenvector of A corresponding to eigenvalue lambda, then X will also be an eigenvector of A inverse corresponding to eigenvalue 1 upon lambda. So, if lambda is an eigenvalue of A, then lambda raised to power k will be the eigenvalue of A raised to power k. For example, if a 3 by 3 matrix is having eigenvalue as 5, 10, 20, then the square of this matrix will be having eigenvalues as 25, that is square of 5, 100 and 400. Moreover, it is very important result for the topic which I am going to introduce you in the next lecture, that is the similarity transformation. So, this result tells us that eigenvectors corresponding to distinct eigenvalues are linearly independent. Moreover, if we do not have the distinct eigenvalues for a given matrix and sum of the eigenvalue lambda is having algebraic multiplicity k, then the number of linearly independent eigenvectors of A associated with this eigenvalue lambda is given by m, and where m is the n minus rank of A minus lambda I. Now, what is the diagonalization of a matrix? So, the eigenvalue and eigenvectors of a matrix having a very important property, that is, if a square n by n matrix A has n linearly independent eigenvectors, then it is diagonalizable. That is, it can be decomposed as A equals to P D P inverse, where D is the diagonal matrix containing the eigenvalues of A along the diagonal. So, D can be written as diagonal lambda 1, lambda 2, lambda n, and P is the matrix which is formed with the corresponding eigenvectors writing in the columns. For example, if you take a matrix this one 2 1 2 3, it is having eigenvalue 1 and 4 and corresponding eigenvectors 1 minus 1 and 1 2 respectively, then it can be diagonalized as 2 1 2 3 equals to 1 1 minus 1 2. So, it is my matrix P, and you can note here I have written this first eigenvector as the first column of P, second eigenvector as the second column of P into D. So, D is a diagonal matrix having the eigenvalue as the diagonal entries. Only thing you have to note down that first eigenvalue is 1 in the first row. So, the eigenvector corresponding to 1 should be the first column. Similarly, 4 is in the second row. So, the eigenvector corresponding to 4 should be in the second column, and then P inverse. So, if you multiply these 3 matrices, the product of these 3 comes out to be this matrix, and hence you this particular property is very important when you are talking about eigenvalues, because the eigenvalue of this A and the eigenvalues of D will be same, and since D is a diagonalized matrix, diagonal matrix, so eigenvalues will be the elements in the main diagonal. Moreover, we can use this property in many other way, like suppose you need to find out A raised to power m. So, this means P D P inverse, P D P inverse, P D P inverse m times, it is coming out to be P into D raised to power m into P inverse, where D is a diagonal matrix. So, D raised to power m can be calculated very easily just by taking the power of lambda 1 lambda 2 m power m, and easily calculated, and hence we can calculate A raised to power m in a very easy manner. However, all the matrices do not have this property, that all the matrices cannot be written in the form P D P inverse. So, in the next class what we will do, we will take some example where some of the matrix I can write as P D P inverse, but some of them I cannot write. I will tell you the condition which is necessary for writing A equals to P D P inverse. I will tell you if I cannot write A equals to P D P inverse, then is there any transformation, other transformation which is which makes this a factorized into product of different matrices. So, now I will stop myself and I will start from the next lecture, that is similarity transformation. Thanking you.